Swayam Prabha. Digital India. Educated India.
Hello, this is lecture number 14 on the design of Ferguson segments and curves. Design of curves, features. A synthetic curve would be composed of lower order or lower degree segments. Here, a cubic segment will be good enough as it would represent variable or linearly varying curvature. There is a reason why we prefer low order or low degree segments, because higher degree segments will have more oscillations or fluctuations, which we don't want. A linear segment will not be good because the slope is constant. A quadratic segment may not be adequate because there the curvature will be a constant. Therefore, a cubic segment will be adequate enough for us. We have also discussed before that each segment should be represented by a parametric equation, and segments would be juxtaposed at junction points. They would be joined together at junction points. While doing so, we need to ensure that position, slope, and or curvature continuity is maintained at the junction points. Let's take a look at an example as to what I mean. Let's say we have a set of data points. The circles represent a different subgroup of data points, and rectangles represent a different subgroup. We are going to be considering these data points in different subgroups when designing a curve segment. For example, the circular data points can be interpolated using this cubic segment. You can as well think of best fitting these 4 data points, doesn't matter. And these rectangular data points will be interpolated or maybe best fit using a different cubic segment. The difference is shown in the color here. These two are different segments. These are the data points specified through interactive input by the user. A user may also want to call them the design points that would roughly depict the shape of each segment of a curve and therefore the entire curve. This point here is the junction point, and it's common to the segment on the left and the segment on the right. As I said before, these are the two segments that constitute this composite curve. Again, data points and our slopes are essentially a designer's choice, and it is here that we need to worry about different continuity conditions like the position continuity, the slope continuity, the curvature continuity, and so on and so forth. Let's talk a little bit about parametric segments. A word about the difference between segments and curves. By segments, I mean individual low degree segments, and by a curve, I would mean the entire composite curve. This is the difference between segments and the curves that I will try to maintain throughout the lectures or throughout the discussion on the design of curves in general. Parametric equation of a segment: the position vector of any point on the curve as a function of parameter u, that is r of u, can be given by x of u times I plus y of u times j plus z of u times k. X of u, y of u, and z of u are scalar functions. in compact vector form, they would be written as an ordered set xu, yu, and zu. We might want to think about modeling x of u, y of u, and z of u each in parametric cubic form. Again, cubic will be adequate enough for us because a cubic form would represent a linearly varying curvature. More the degree, more the oscillations. X of u may be written as a0x plus a1x times u plus a2x times u squared plus a3x times uq. a0x, a1x, a2x, and a3x are unknown coefficients that we'll determine later. Likewise, y of u and z of u, the two other scalar functions, can be modeled in a similar manner. Once again, coefficients a0y, a1y, a2y, a3y, and a0z, a1z, a2z, and a3z are unknown coefficients. In general, coefficients aij, which represents all these coefficients, 12 in number, need to be determined. I can write these equations in matrix form. If I use this ordered notation for R of u, we have R of u equals xu, yu, zu in 1 by 3 vector notation, which will be equal to u cube, u squared, u, and 1. This is a 1 by 4 matrix having different degrees in u. This is the coefficient matrix. In short, this matrix is represented by capital U, and this coefficient matrix is represented by capital A. Coming on to Ferguson or Hermite segments, as they are called. Let's say a designer specifies two data points, pi with coordinates xi, yi, and zi, and pi plus 1 with coordinates xi plus 1, yi plus 1, and zi plus 1. In addition, he or she also specifies the slopes at these data points. The slopes are denoted by t sub I and t sub I plus 1. The x, y, z components are pi, qi, ri, and pi plus 1, qi plus 1, and ri plus 1. A typical Ferguson or Hermite segment will look like this. It would pass through these data points, and these slopes will be tangent to the curve at the endpoints. At point pi, the parameter value u is 0, and at point pi plus 1, u equals 1. All the points on this curve will be for different values of u in between 0 and 1. As I said before, the input would be the endpoints and slopes from the designer. We have, therefore, 4 conditions, 2 points and 2 slopes for each of the x, y, and z. Now let's consider the scalar function x of u. If you notice, we have 4 unknowns here. 4 conditions, 4 unknowns. This is solvable. Going further, for u equals 0, x of 0 is xi, x of 1 is xi plus 1, for u equals 1, dx over du evaluated at u equals 0 is pi, and dx over du evaluated at u equals 1 is pi plus 1. These are the four conditions that can be used to determine these four unknowns. The rest is algebra. On substitution, we get these equations. X sub I equals a0x, x sub I plus 1 equals a0x plus a1x plus a2x plus a3x, pi equals a1x, and pi plus 1 equals a1x plus 2 times a2x plus 3 times a3x. I can solve these four equations and get the four coefficients. A0x equals xi, a1x equals pi, a2x equals 3 times delta xi minus 3 times pi minus delta pi, and a3x equals delta pi minus 2 times delta xi plus 2 times pi. Delta xi is xi plus 1 minus xi, and delta pi is equal to pi plus 1 minus pi. If I substitute those coefficients back, the scalar function x of u will become x of u is equal to xi plus pi times u plus, within parenthesis, 3 times delta xi minus 3 times minus delta pi times u squared plus delta pi minus 2 times delta xi plus 2 times pi, all within parenthesis, times u cubed. We can think of rearranging the right hand side here so that we can group all terms involving u and all terms involving x's and p's, the geometry that the designer had specified. Once we regroup this, the coefficient of xi is 1 minus 3 times u squared plus 2 times u cubed. The coefficient for xi plus 1 is 3u squared minus 2u cubed. That is u minus 2u squared plus u cubed, and that of pi plus 1 is minus of u squared plus u cubed. What we can do is we can represent these coefficients as functions h. h03 of u times xi plus h13 of u times xi plus 1 plus h23 of u times pi plus h33 of u times pi plus 1. The subscripts over here, they represent the index, and the superscripts represent the degree of each of the functions. h03 is this function here, which is cubic. h13 is this function, again cubic. h23 is this function, and h33 is this function. All the h's happen to be cubic in U. I can represent this statement in compact matrix form. X of U is a 1 by 4 matrix involving U cube, U squared, U and 1. This is a 4 by 4 coefficient matrix, and if you notice, these numbers come from here. And this column vector represents the x coordinates of the 2 points and the x components of the 2 slopes at the 2 points. respectively. Likewise, if you think about it, the scalar function yu will have a very similar form. That is, the Hermite functions h03, h13, h23, and h33 will be identical. Only the geometry changes. Here, the geometry will involve the y coordinates and the y components of slopes. Likewise, for the z as well, the scalar function zu will use the Hermite functions and the geometry corresponding to the z direction, the z coordinates at 2 points and the components of the z slopes. In matrix form, I can combine all the information pertaining to the x, y, and z coordinates. In ordered form, xu, yu, zu is r of u, the position vector of a point, and that will be equal to this 1 by 4 matrix u cube, u squared, un 1. The coefficient matrix will be identical in all the 3 cases, the entries being 2, minus 2, 1, 1, minus 3, 3, minus 2, minus 1, 0, 0, 1, 0, and 1, 0, 0, 0. And the geometry pertaining to the x, y, and z coordinates will be arranged column-wise. This is a Ferguson cubic segment for you in matrix or compact form. If I look at this row here, this row represents the position vector of pi. The second row is the position vector pi plus 1. The third row is the first slope ti, and the fourth row is the second slope ti plus 1. In more compact notation, this matrix is represented by capital U in bold. This 4 by 4 coefficient matrix is represented by capital M, and this column vector, which is actually a 4 by 3 matrix, represents the geometry specified by the designer, G. As I mentioned, U is of the size 1 by 4, M is of the size 4 by 4, and is called the Ferguson or Hermite coefficient matrix, and G is of the size 4 by 3, the geometry matrix. Once we know the scalar functions xu, yu, and zu, computing the derivatives of a Ferguson segment should be straightforward. At any point, the first derivative is given by r super u of u, which is dr over du, which is 6u squared minus 6u times pi plus minus the 6u squared plus 6u times pi plus 1 plus 3u squared minus 4u plus 1 times ti plus 3u squared minus 2u times ti plus 1. These are straightforward results that we get by differentiating the Hermite functions with respect to u. In matrix form, dr by du or r super u of u is given by u cube, u squared, un 1. The coefficient matrix will have the entries 0, 0, 0, 0, 6, minus 6, 3, 3, minus 6, 6, minus 4, minus 2, 0, 0, 1, 0. And this is the geometry matrix that we have seen before. Notice that u is quadratic in all these 4 functions, because of which the first row has all zeros. If you compute the second derivative, R super uu of u, which is d2r over du squared, and that is given by 12u minus 6 times pi plus minus of 12u plus 6 times pi plus 1 plus, within parenthesis, 6 times u minus 4 times ti plus 6u minus 2 times ti plus 1. Notice this expression and differentiate only these terms, assuming that the design information pi, pi plus 1, ti and ti plus 1, they do not vary with respect to u. In matrix form, the second derivative is given by u cubed, u squared, u and 1, 1 by 4 matrix. The coefficient matrix will change and will have the entries 0, 0, 0, 0. The second row again zeros. The third row is 12, minus 12, 6, 6, and the fourth one is minus 6, 6, minus 4, minus 2. This coefficient matrix is represented by m sub 2, while this one here is represented by m sub 1. The geometry matrix G remains unaltered. Why do we need derivatives? Well, we want to compute the differential properties of a curve at any point. And in particular, we would like to impose position, slope, or curvature continuity at junction points, the points which are common between two Ferguson segments. Composite Ferguson curve. This would be a sequential juxtaposition of individual Ferguson segments. Say we have the first data point, the second data point. The position vector is pi with coordinates xi, yi, and zi. Here, the position vector is pi plus 1 with coordinates xi plus 1, yi plus 1, zi plus 1. The slopes are ti and ti plus 1 with components pi, qi, ri, and pi plus 1, qi plus 1, and ri plus 1. These are the directions of ti and ti plus 1 respectively, and this is how a Ferguson segment between the 2 points may look like. If a designer chooses to represent this segment by r super 1, this number here denotes that this is the first segment, and this variable u1 represents the parameter only for this segment and no other segment. u1 equals 0 at point pi, and u1 equals 1 at point pi plus 1. If a designer chooses to specify another point, let's say pi plus 2 with coordinates xi plus 2, yi plus 2, and zi plus 2, and also a slope at this point ti plus 2 with components pi plus 2, qi plus 2, and ri plus 2. The second Ferguson segment would probably look like this. Let's represent this segment by r super 2. This number represents this segment. This segment will have a different parameter, u2. u2 and u1 are not the same. For u2 equals 0, the point on this segment is pi plus 1, and for u2 equals 1, the endpoint is pi plus 2. Note that u1 and u2 both are supposed to vary between values 0 and 1. In other words, u2 greater than 1 will have no bearing on this portion of the composite curve, and u2 smaller than 0 will not affect the shape of this segment. Now, C1 composite Ferguson curve, or C1 continuous composite Ferguson curve. Let's keep this diagram here. Notice that this point is common between these two segments, R super 1 and R super 2. For position continuity or C0 continuity, we need that the junction point between the two segments is the same. In other words, the end point for u equals 1 for the first segment should be the same as the start point for R2 at u equals 0. This is this point right here. And for slope continuity or C1 continuity, the junction slope should have the same direction. Note that the two slopes here may or may not have the same magnitude. In other words, if the first derivative of R1 with respect to its parameter u evaluated at 1 represents the slope for this segment here, and if the first derivative of R2 evaluated at u2 equals 0 represents the slope here for this segment, then alpha 1 times dr over du at 1 is equal to alpha 2 times dr over du at 0 for this segment, equal to a vector small t, the unit tangent. Alpha 1 and alpha 2 are the normalizing scalars, and t is the unit tangent vector at the common point or the junction point. It is not very difficult to observe that Ferguson curves are inherently position and slope continuous if intermediate points and slopes are used by two contiguous Ferguson segments. To re-emphasize, this is because the junction points and the slopes will be the same between the two contiguous or adjacent segments. Let's consider an example. Given two data points, let's say pi as minus 2, 2 and pi plus 1 as 6, 7. And the unit tangents t sub I as 0.94, 0.35 and ti plus 1 as 0.39 and minus 0.91. These are the components such that ti and ti plus 1 are both unit tangents at pi and pi plus 1. Let's have the tangent magnitudes ci at pi, the first point, as 8.5 and ci plus 1 as 15.2 at the second point. Recall that we are only interested in matching the tangent directions and not the magnitudes. In other words, these magnitudes can be additional design choices for us. Questions. What would be the tangent, the radius of curvature, the normal, and the binormal at parameter value u equals 0.5 for the segment? Let's try to find out. We have capital Ti as small ci, which is this value, times the unit tangent Ti here, and capital Ti plus 1 equals ci plus 1, which is 15.2, times the unit tangent ti plus 1. In short form, t of u is the first derivative of r with respect to u, which is equal to the u matrix times the coefficient matrix m1 times g. Here are the details. U is u cubed, u squared, un1. M1 is this 4 by 4 coefficient matrix, and G is the geometry matrix. Note that minus 2, 2 is point pi, 6 and 7 is point pi plus 1, 8 and 3 would be Ti times Ci, and 6 minus 14 will be Ci plus 1 times Ti plus 1. If we work out the algebra, which is not very difficult, we will observe that T of u, the tangent at any point on the segment, will be of 6 u squared plus 4u plus 8 times the unit vector I along the x direction plus 63 times u squared plus 46 times u plus 3 times j, and this is r dot. If we differentiate this expression again with respect to u, we'll have r super uu, which is dt over du, as minus of 12u plus 4 times I plus minus of 126 times u plus 46 times j, and this is r double dot. Evaluating t at u equals 0.5 will therefore give us r dot at 0.5, which would be 8.5 I plus 10.25 times j. The magnitude of t can be determined as 13.32. This is not difficult. The unit tangent, therefore, will be this vector over this magnitude. Likewise, we can get r double dot at u equals 0.5 as minus 2 times I minus 17 times j. Now, for the curvature at a point kappa, from coordinate geometry, we would know that kappa is given by mod of r dot crossed with r double dot over mod of r dot the whole cube. We know what r dot is. We also know what r double dot is. Computing the cross product is not very difficult. The magnitude will come out to be 124. We know what r dot is, so kappa is 124 over 13.32 the whole cube, which would mean that the radius of curvature is 1 over kappa, which is 19.06 at u equals 0.5. Now for the binomial b. The binomial b is given by r dot crossed with r double dot over the modulus or the absolute value of the numerator. Recall from the previous lecture that we had expressed b in terms of the derivative of r with respect to s, the arc length parameter or the natural parameter. Let me explain this to you on board. Recall that the unit tangent t has the direction of dr over ds, which is r prime, and n is defined of d2r over ds squared, which is r double prime. Notice also that t and n are perpendicular, and a vector binomial is perpendicular to both t and n, because of which b is represented as the cross product between the unit tangent and the unit norm. Now let's observe or work out how to convert information that we have with respect to the arc length parameter s in terms of parameter u. In other words, let's work to get r primes in terms of r dots. In other words, let's work to get derivatives with respect to s convert to derivatives with respect to u. Now, r prime is dr over ds. Notice that I'm using the vector notation here. By chain rule, this is equal to dr over du times du over ds. This part is a vector, this part is a scalar. By notation, this is r dot times du over ds. If I differentiate this the second time with respect to s, I have r double prime equals d over ds of this expression here, which is dr over du times du over ds. If I work out the expression, this would be equal to d over ds of dr over du times du over ds plus r dot times d2u over ds square. This differential operator will first operate on this and then it will operate on this. I can incorporate or use the chain rule again here. I can multiply and divide by du here, so that this term will become r double dot times du over ds the whole square plus r dot times d2u over ds square. So now we have r prime in terms of r dot, this being a scalar, and also we have r double prime in terms of r double dot and r dot. If you look at these three expressions here, the binomial b will have the direction given by r prime crossed with r double prime. I'm using here the proportionality sign. Once I get the direction, I can always divide this expression by its magnitude to get the unit vector or the unit binomial. Now let's see what r prime crossed with r double prime is in terms of r dot and r double dot. R prime crossed with r double prime is this term here crossed with this term here, which will give us r dot crossed with r double dot times du over ds the whole cube, which is a scalar, plus 0. Notice that r dot crossed with r dot will be 0. This expression here conveys to us that the direction given by r prime crossed with r double prime is the same as the direction given by r dot crossed with r double dot. Coming back, the binomial B is given by r dot crossed with r double dot over the magnitude. If you work out the algebra, this is simply minus of k, which is quite straightforward because the segment that we are considering lies on the xy plane. The normal then is given by b crossed with t here. Notice that the magnitude of this is not unity, so we'll have to divide t by its magnitude to get the unit tangent here. If we work out the algebra, this is, or n is given by minus of 0.64 times j plus 0.77 times I. The torsion is given by the relation r dot crossed with r double dot, this entire vector dotted with r triple dot over the absolute value of r dot crossed with r double dot, the whole square. It would not be difficult for us to determine that the torsion of the curve is 0. Physically, one might think of tau representing the out of plane warp, a local warp of a curve. You might want to work out the derivation of this expression as an assignment. Let's consider an example of C1 composite Ferguson curve. We are given 4 data points: A with coordinates 0, 0, B with 2, 5, C with 3, 1, and D with 7 and minus 3. And the designer also specifies the respective 4 slopes at these design points: 30, 15, minus 15, and minus 45 degrees. We need to determine the C1 continuous Ferguson curve. We know that dy over dx is tangent of theta, the slope. We can rewrite the slope equation in this form: dy over du equals dx over du times tangent of theta, and we can assume dx over du as 1 and then compute dy over du accordingly. This table summarizes the entire geometric information provided by the designer: the coordinates of the 4 data points, the individual slopes. Notice that dx over du, the x component of slopes at all the 4 data points are 1. The y components of these slopes are computed. We have seen before in this lecture. We can work out the expression for the first segment, the second segment, and the third segment. This matrix here would be with respect to different parameters u1, u2, and u3. The 4 by 4 Ferguson matrix will be identical for the 3 cases, and the geometric information will differ. This geometric matrix corresponds to the first and second data point. This one here corresponds to the second and the third, and here the last one corresponds to the third and the fourth data point. The slopes are mentioned respectively. Let's observe how the composite Ferguson curve looks. This is the first data point, the second data point, the third data point, and the fourth data point. This is the first decide to relocate any one of these data points, how do we expect to see the changes in different Ferguson segments? You would observe that the third segment will change like so, and the second segment will change like this. The first segment will not change in shape. Once again, this point moves, the third segment changes in shape, and the second segment changes in shape as well. In general, C1 continuous Ferguson curve will exhibit local shape control properties. For example, if I now decide to relocate this point here, only this segment and this segment will change, while this segment will remain intact in shape. Now for C2 composite Ferguson curve. Here we consider curvature or C2 continuity, as we call it. For that, at the common junction point, the curvature information from the segment on the left and the segment on the right should be the same. That is, the curvatures from the left segment and from the right segment should be identical. We know that curvature is given by r dot crossed with r double dot over r dot the whole cube. For the first segment, the curvature is dr over du crossed with d2r over du squared, both evaluated at the parameter value 1 over mod of dr over du the whole cube. An identical expression is to be used on the right hand side. The only difference is that the segment is the second segment here, and the information is evaluated for parameter value 0. We know from C1 continuity that dr over du for the first segment evaluated at 1 equals the unit tangent over the corresponding normalizing scalar, and dr over du of the second segment at u equals 0 is equal to t over alpha 2, the unit tangent over the corresponding normalizing scalar. Notice that while I'm using u here, I primarily mean that this parameter is different from this parameter. And this is implicit throughout this lecture. If we plug in this condition into this condition, we will get t crossed with d2 r1 over du squared evaluated at 1 equals alpha 2 over alpha 1 the whole squared times t crossed with d2 r2 over du squared evaluated at u equals 0. To re-emphasize, it should be kept in mind by the student that the two parameters for the two segments are different, even when notationally I have used u here, common to both. Nevertheless, one of the conditions that would satisfy this expression here is given by d2 over du squared of the first segment evaluated at 1 equals alpha 2 over alpha 1 the whole square d2 over du squared of the second segment at 0 plus some scalar mu times the first derivative of the second segment evaluated at 0. Why would this condition satisfy this expression here? Let's see. We would know that t crossed with the first derivative of the second segment at u equals 0 will be 0. This is because the direction of the unit tangent will be the same for the first segment and the second segment at the common junction point. You can satisfy yourself by plugging the expression for this term here. This term here will give you this term, and no matter what the value of mu is, t crossed with the corresponding slope will be 0. If we further impose the normalizing scalars to be equal and mu to be equal to 0, then the curvature continuity condition simplifies to the continuity of the second derivative, that is d2 over du squared of the first segment at u equals 1 equals d2 over du squared of the second segment at u equals 0. This is relatively more strict. A non-zero value of mu will give a designer an additional design choice. Recalling from the previous slide that the second derivatives of the two contiguous Ferguson segments are equal, we have d2 over du squared of r of u in general equals pi times minus 6 plus 12u plus pi plus 1 times 6 minus 12u plus ti times minus 4 plus 6u plus ti plus 1 times minus 2 plus 6u. Noting that the second derivative of the first segment at u equals 1 equals the second derivative of the second segment at u equals 0, we get 6 of pi minus 6 of pi plus 1 plus 2 ti plus 4 times ti plus 1 equals minus of 6 times pi plus 1 plus 6 times pi plus 2 minus 4 ti plus 1 minus 2 ti plus 2. How did we get this equation? The first segment has data points pi, pi plus 1 and slopes ti and ti plus 1. For the first segment, u should be 1. So if you look at the left hand side of this equation, we have 6 times pi minus 6 times pi plus 1 plus 2 times ti plus 4 times ti plus 1. For the second segment, the data points will be pi plus 1, pi plus 2, and the slopes will be ti plus 1 and ti plus 2. In other words, the index here needs to be incremented by 1. Also, these coefficients need to be evaluated for u equals 0. Once done, the right hand side can be obtained. One can rearrange these terms here to get ti plus 4 times ti plus 1 plus ti plus 2 equals 3 times pi plus 2 minus 3 times pi. Now this is an equation corresponding to all values of I going from 0 1 up till n minus 2, that is for n plus 1 data points. This equation here, or in fact these n minus 1 equations, relate n plus 1 data points and n plus 1 slopes. These n minus 1 equations ensure that intermediate slopes are no longer free choices, but they need to be computed if the continuity in second derivative is to be maintained at the junction points. Since we have n plus 1 data points and n plus 1 slopes, and since we have n minus 1 equations here, we have two free choices for the slopes. We can use the first and the last slope as free choices, and we can specify them. And all the other intermediate n minus 1 slopes will then be computed using this set of equations. If you also closely notice, this would be a linear set, a linear system, and this would be a tri-diagonal system, which would be very efficient. For example, we have data points A with coordinates 0, 0, B with 1, 2, C with 3, 2, and D with 6 and minus 1. And let's say we have slopes respectively as 45 degrees, 30 degrees, 0 degrees, and minus 45 degrees. We need to determine C2 continuous Ferguson curve. Let's use the free choices, the first and the last slopes as 1, 1 and 1, minus 1. With that, we compute the intermediate slope. We have T0, that is 1, 1, plus 4 times T1 plus T2 equals 3 times P2, which is 3, 2, minus 3 times P0, which is 0, 0. And T1 plus 4 times T2 plus T3, which is 1 minus 1 here, equals 3 times P3, which is 6 minus 1, minus 3 times P1, which is 1, 2. Note that I have written these equations with both x and y components. Working out the algebra should not be very difficult from here on, and we should be able to compute the intermediate slopes T1 and T2. Once we do that, the first segment R1 is 0.2 times u1 cube minus 0.4 times u1 squared plus u1, the x component. The y component would be minus 1.13 u1 cube plus 2.13 u1 squared plus u1. Likewise, the second segment is 0.4 times u2 cube plus 0.4 times u2 squared plus 1.2 times u2 plus 1, the x component, and the y component is minus 0.6 u2 cube minus 1.27 u2 squared plus 1.87 u2 plus 2. The third segment can be likewise computed. Let's look at the graphics here. But before that, if we decide to relocate an intermediate point 3, 2 to a different position 1.54, notice that we would need to recompute all the intermediate slopes. Once again, the algebra is very similar. This is the first segment of the recomputed composite Ferguson curve, the second segment, and the third segment. I'm skipping the algebra, assuming that you would be able to work it out nicely. Now the graphics. The first 2 points and the first cubic segment, the third data point, the second cubic segment, the fourth data point, the third cubic segment. This is the original C2 continuous Ferguson curve. And I emphasize here that at these junction points, the second derivatives will be continuous. If I decide to move this point to a new location, the first segment of the new composite curve will be this. This would be the second segment, and this would be the third segment. This simple relocation forced us to recompute the intermediate slopes over here, because of which the shape of the entire composite curve changed. In other words, C2 composite Ferguson curves do not have local shape control properties.